Okay, we are starting with the sixth chapter of the Koenig and Ritchie C language book. And today we're going to be learning about structures. We're going to be going over the mini codes for the homework. But before we get to that, I would like to go over some easier examples so that we can get accustomed to what exactly is a structure and how to access information in a structure so that we won't struggle as much with the example codes here. So let's make a very large terminal. And I've made some student record examples here. Let's look at the first one. So I am here defining a data structure. I'm calling it estudiante, student. Each student has two associated values. The student ID number, I'm putting it as an unsigned integer because our university is using numbers for this. So it could be, for example, 1, 2, 3, 4, 5, 6, 7. These are always going to be 7 digits, and sometimes people have a 0 in front when they're like students from like a very long time ago. So we might need to be able to print those out correctly, but we're going to store them without deleting zeros. And I'm making a pointer to a character array here. So this is going to be a string that's going to store the study program. And I'm going to use the 3-letter abbreviations here. The 3-letter ones are the ones that the inscription system's using. I am aware that some programs, like the mechatronics program, it's managed by a 3-letter one and a 4-letter one in different contexts. So this thing here says that I want variables of the type student to contain two subvariables, so to speak, the student number and the study program. Here I am saying that instead of always writing struct estudiante, I would like to just say alumno. So then I'm saying also that I'm going to have a subroutine that doesn't return anything. It's going to be called imprime, and it's going to take an argument alumno. So it's going to be a routine to print student information. Let's briefly check this in a poll. So what we're trying to learn here is you can make a struct something that's going to have fields. The fields are going to have their own data types. And then we can use the type def to give a nickname to the struct something so that we don't have to write the word struct anymore. Then we can just refer to struct estudiante as alumno. Okay, looks like we have the situation under control. So now let's look at the C code I made to go with this. So I'm including the standard input and output. This is included for printf. And I am including our new header. So in main, I'm saying I would like to have a variable of the data type alumno. It's called fulano. So now fulano has fields. I can use the dot to access those fields. Dot matr is going to refer to this field here, the student number. And the .pe is going to refer to the study program, Programa Educativo, and I can assign string literals and integers there. And if I only put 6 digits, I'm going to assume that it should actually be a 7-digit number with a leading 0. So here I'm going to say that when I print the student ID, I always want to print it with a 7-field length, and I want to put zeros in front if it's not 7 digits long. So let me make another tiny terminal here so we can compile and run this program. So now I only have the one variable fulano First, it's 0, 1, 2, 3, 4, 5, 6, 7, and it's a software engineering person. And then that same variable gets changed into 1, 2, 3, 4, 5, 6, 7, and becomes a mechanical administrator. But that's just one single variable, and I am putting in that variable a different value on top of the previous one. So this is what it prints out the first time, and then I change the fields, and this is what it prints out the second time. We're going to make another poll. Okay, I'm getting some messages of pending gradings. So I'm going to register those while you guys vote on the poll. I really wish Daniela would have told me her student ID, but I'm going to fix this from some older message. If you guys follow the instructions, everything's so much faster and easier. It's also going to take us less time to get things done if everybody follows the instructions. Okay, so it looks like we're okay. A couple of people are still slightly confused, so let's revisit this. I can give here names to the fields, and then when I want to access a certain field, I use this dot to access the field. So I can't assign anything to Fulano as such. I have to assign to its fields because Fulano has these two fields. So I do not have a variable that would just be PE or MATR. I only have the variable Fulano that contains the sub-variables accessed by this dot notation. And this is simply print the first field always with 7 digits, add leading zeros to fill the digits if they are fewer. I'd like to know what questions we have about the examples thus far so we can clarify the questions and then move on. If you don't want to type your question, you could also say it on Discord. I can still hear you. I'm just muting myself so that you guys don't hear me double. Yeah, we're going to have several. We're going to actually make an array of students later on. But at this point, we're just trying to understand that structures have named fields. I can make a type def so that I won't have to always type struct estudiante. I could do that as well. Let's actually modify this. Let's call him Wei. So now this guy could be Wei. So now we have Wei and Fulano. Let me find my terminal window. This one. Let's compile it again, run it again. So now I have alumno Fulano and struct estudiante Wei. They're both the same data type. I'm using the type def here to make it look prettier, and I'm not using the type def here. pushing this to the repository, checking for any other questions on Discord. Okay, since we don't have more questions, I'm going to move on to the next version of this example. Keep typing your questions if you have any. So let's go to a second version of the header file. Actually, I'm going to put it here to the side so we can compare. So now I've made a second version of the header file. I have added a third field here. It's going to be an access counter. We're going to count how many times the student information has been accessed. And I have changed this so that the printing is now going to use a pointer. In chapter 5, we learned about pointers. So we now know that when you pass a pointer to a subroutine, the subroutine is actually going to be able to modify the variable. Whereas when you don't pass the pointer, the subroutine is going to be working with a copy of the information. If you have a large structure, you might want to pass the pointer even if you don't actually plan to modify the information, just because it would mean copying a lot of information. So if there is a very large struct that contains a lot of stuff, even if you don't want to modify it, you might still want to use a pointer to print it so that you won't have to copy all the information to the subroutine, but the subroutine is going to access the same version that it exists in the main. So I'm going to show you the second version of the C file to see how this is working. So now I'm using the second header file. I'm still making my alumno fulano just the same way. I'm initializing the counter as a 0. Then I assign the study number, student number. Let's put some other student number here. I make a study program. Then I make a first access here. Then I modify the study program, and then I make a second access here. And the printing is first going to update the access counter so that we know how many times this student has been printed. And I am here printing the student number, the study program, and information on how many times has the student's information has been accessed. So now, if we compile this version, wrong click, come back. The first time we print it, it's the first access because the access counter started as a 0. In the beginning, the printing accesses the field and changes it. And then the second time we go in, it's already going to be a second access. What are the important changes here? I am no longer giving the subroutine the structure. I am giving a pointer to the structure. And since I'm working with a pointer, I'm not using the dot to access the field. I have to use a little arrow. It's made of a dash and a greater than sign. So the little arrow says go to this structure pointed to by this pointer and to this particular field. So it's going to go to the field C and it's going to increment the value of the field C. Here it's going to access the fields of the student number and the study program and the counter using the arrow, since A is not a structure, it's a pointer to a structure. So this is an important thing to remember. You use a dot if it's a variable as such, and you use the little arrow if it's a pointer to a struct. So essentially, we're accessing the fields the same exact way, except that the notation changes when it's a pointer. When it's a pointer, we put the arrows. When it's the raw variable per se, we use the dot. Okay, either the confused people have given up or they have suddenly gained some clarity. Okay, let's go to a third version. So now I make a third version of the C code. I'm still going to use the second version of the header code. And what I'm doing here is that I am now making an array of students. So let's suppose I have a group that can hold 3 students. I can here define an array that I'm going to have an array called grupo of the type alumno that's going to have a cupo number of structures of the type students in it. Then I have an integer I, so I can for loop over the array, and I can initialize all the fields to 0. Now, the grupo as such is a pointer, but the grupo ith element is a variable, so I can use the dot notation to access the fields. Another interesting thing we need to remember from chapter 5 is that if I add an integer to the array, I'm actually obtaining pointers to the elements. So I can just send grupo plus I to imprime, and now that's going to be a pointer to that element in the array. And imprime looks exactly the same it looked the last time. I'm printing the same information using the arrow notation because I am receiving a pointer. Running this one. So now when I access the students, they all have their first access because every student has their own student ID, own study program, and own counter. So when I update the counter for one student, it doesn't affect any of the other students because I have an array of independent students. Okay, so let's check in a poll if we're okay with this. If you struggle still with arrays, please reread chapter 5, because if you don't understand arrays, you're not going to understand arrays of structures either. Okay, it looks like we're largely okay. A couple of people are still confused. If you have a question, please type your question. So the important things to remember, you can use struct to define a new structure. You can use typedef to give it like a nickname to make it a little shorter. You can use the dots to access the fields. If you have a pointer to the structure, you're going to use the little arrow instead of the dot. And you can make an array of structures just as you could make an array of integers or characters. We might be okay. So let's put this away for a second and try to understand the mini codes. Let's put this one away as well. So in the exercise 6, we have small codes, and they, of course, have to do with structures. So let's look at these. In the very first one, I'm making a structure that is a bank account. And here, notice I am combining the information. I'm saying that there's a struct account that has fields username and balance, and I want to call it ACC, short for account. So I've actually written in 4 lines here what could have been 5 lines. I could have first made the struct account char username double balance, and then on a separate line, type def struct account ACC. But I put it all together. It's the same functionality, just a little bit shorter, so that now I can define a subroutine of making a bank transfer. I'm going to put a pointer from which account the money is coming from, a pointer to which account the money is going to, and how much money this is. It's really important these are pointers, because remember, if they're not pointers, then we're working with copies and nobody's actually getting any new money and nobody's actually losing any money, because I would just be fiddling with the copies. So here I'm saying that if the account from which I'm transferring has enough money for the transfer, so meaning it won't be zero balance, then I will sum the money to the target account and I will take it away from the origin account. If there isn't enough money, I'm not going to do anything at all. And then I have a second subroutine, display. It's kind of like the printing routine. It's simply going to say, what's the username and how much money does this user have? Then in my main, I am saying I am going to have an account. Account A, the user's foo and has A amount of money. In account B, the user's bar and has B amount of money. The higher amount is going to be, the higher pointer is pointing to that account that has a higher balance, and the lower account is pointing to the one that has a lower balance. Then I'm checking how much is the difference between the high and the low account. Then I'm going to make a transfer, and then I'm going to print out the balance for both accounts A and B. So on my data, it says that account A should have $200 on it, and account B should have 40. And what I want to put here is the code necessary to make it so that both accounts have the same amount of money in the end. So you just have to do a little bit of math with the difference. How much of the difference do you need to transfer from which account to get both to the same balance? Let's check in a poll if we are comfortable with the code for this first exercise. Remember that this is just a short way of doing an if-else. If this condition is true, the high account will be the pointer to A. If this is false, then high account will be pointer to B. And here it's vice versa. So the higher one ends up being high and the lower balance one ends up being low. Okay, 10 people are okay with this one. Still no questions, but some people need more time. The second one here, I have here a comparison function. It's taking 2 pointers, it's comparing those pointers. Then I am going to pass this function to qsort as a function pointer. And what we want is to define what the data is going to initially have. This is simply a reservation of memory, and this is where I'm liberating the memory. So this is actually revisiting stuff from chapter 5, similar to what was going on in the previous chapter. Please read here very carefully what's going on in the data, so that you initialize in such a way that the code is eventually going to do what it says here. And in the third one, what we have is an enumeration. An enumeration is a thing where I can give names to values. So when I'm saying I want to have an enumerator that can either be false, that's a 0, or true, that's a 1. Then I'm using the type def to say that I would like Boolean to be a data type that has this enumeration, so that Booleans can either be false or true. Then I have here a little code that's actually using this Boolean kind of data. It's running over the command line arguments. It's doing things to them. And what you're going to want is to provide the command line arguments to make the program print this. So there's nothing missing in the program. There's no 3 dots in here. You want the program to print this, and you need to figure out what do you need to give as command line arguments. What do you need to type after the name of the executable to make it print this? So here the first mini thing has to do with, did I understand structs? The second one has to do with, did I really understand how to reserve memory for arrays? Did I really understand function pointers? And the third one has to do, did I really understand type def and enumerations? Did I really understand command line arguments? And do I have any idea what's going on in this code? So in the first one, you substitute the 3 dots. In the second one, you substitute the 3 dots in here. And in the third one, there's no 3 dots. You just need to say what would be the command line argument to make that code print this. Okay. Let's make a poll of all these mini questions. If we're semi-okay here, I want to go to the whiteboard to discuss a wonderful thing called a binary tree. So we could make a little example of a binary tree, and that would really help you with the 6th homework, because that's going to be a tree. That's not actually going to be a binary tree. It's very related to the examples in chapter 6, but I would like us to make a little tree of our own before you guys trying to make the tree form the homework. I don't see anybody typing questions, so I'm heading to the whiteboard. Okay, so a binary tree is a way to store information in an ordered fashion. We're going to be storing positive integers to make our life easy. So when I have a new tree, an empty tree that doesn't have anything yet, the first thing we're going to put into the tree is going to be the root of the tree. So this one we call root. It's the first node that exists. If I add something smaller than the root to the tree, it's going to go as a left child of the root. If I add something larger than the root, it's going to go as a right child of the root. Then if I add something that's smaller than the root but larger than 8, it's going to be in turn a right child of the left child. So now it's a grandchild. And these things are called leaves, the ones that don't have any children. And if a node has both of its children, that node is full. So this one's now also a leaf. So we're going to make a data structure that allows us to do this and lets us add information. If we try to add a number that's already there, nothing's going to happen. If we want to, we could have a counter that if I add a second 23, I'm just going to update the counter here. And if I add 17 4 times, I'm just going to end up having a counter 4 here. Then if I want to delete something, I could reduce the counter. And if the counter went to 0, then I would get rid of the node altogether. So this is what I want to write like live, like right now as code, so that we get an idea on how to make this kind of a structure. So basically, this is going to be a node, and the node's going to have children that are also nodes. So it's like a recursive data structure definition. So let's try not to make a giant mess of this. Let's try to make a binary tree, put it in one source file here so that we can easily look at all of it. So what will the nodes look like? Let's make the type def straight up so that it's going to be shorter. So the struct's going to be called tree node, but I'm just going to call these nodes. They're all going to have a value. We can do the version with the counters. And then I'm going to have a struct tree node pointer to the left child and a struct tree node pointer to the right child. Let's compile this. Works fine. So now, if I want to start adding things to this, I'm going to need to keep track of where my tree is. So here I could say that I have a node pointer that points to the root. Then I would want to let the user add stuff to the tree. So we can make here a little while true. That's going to contain a switch case. We could have here a character that we're going to take as an argument. Let's suppose that if we type a Q or an uppercase Q, that we're going to break the loop. In any other case, actually, let's put character values here. It's going to be less code if we put character values and integer counters. Actually, let's use the letters as values and let's use a dash to break. So we would want to insert the character into the tree. Let's actually call this one tree. And in the beginning, it's not pointing to anything. And actually, we're just going to put the return 0 here so that we enter the exit the entire program when we type the dash. And anytime we insert anything into the tree, then we could show the tree afterwards. So now we need to worry about two things, how to insert and how to show. We could actually make it so that we only show when there is a successful insertion. If there isn't, then we don't really show anything. So let's make a subroutine to insert, and then let's make a subroutine to show. If I want to print anything, I'm going to need a library. And if I ever want to reserve any memory, I'm going to also need the standard library here. So from here, we're taking the printing. From here, we're going to take the reserving and liberation of memory. If the position isn't null, we're actually going to print something. If the position is null, meaning there's nothing there, then we're not going to print anything. So what would we print? We could print the value followed by the counter. And then we could print the children. So if left child to this position isn't null, we would print it. But since we're already checking if position is null, it's much easier just to recursively say that let's show these positions left child. And let's also show these positions right child. And let's make it so that the insert doesn't really do anything yet. It just returns 0, just so we can compile and see if everything's under control. Let's put this a little higher here. Okay. I wrote left, right because I'm very clever. Right child. Treat the string as an argument to avoid this format string. Okay, I need to put the double quotes. I'm really good at typing single quotes, and I'm really good at forgetting what I'm supposed to be printing. So we're supposed to be printing the value and the counter. Okay, it doesn't seem particularly unhappy. Probably not going to do anything very reasonable, except quitting when I type the dash. So now if we actually want to insert things into this tree, we need to do a recursive thing. We're first always inserting into the root. If the root doesn't have a value yet, then we should put a value to it. So if the position we're pointing to is presently null, meaning that there's nothing there yet, then we should totally create something there. Let's do it the ugly way here first. So I'm going to reserve space. That points to one node. Compiling to see if I broke something. Size off, missing an E. The E on my keyboard is not very reliable. And then, since we reserved this space, we could just put the value there. And we could set the counter as 1. And we don't have to do anything else because this was our first node. Okay, and then we could return a 1 because we actually had a successful insertion. Let's look at what this looks like. So if I put an F there, how did this go? If insert C3 gives a positive, then we show tree. And if position isn't null, actually, no, I have to return this here. I need to return. Actually, I don't have to return anything if I take a pointer to the pointer. Let's see if I'm breaking everything. So when I insert, I need to give it the address of this pointer. And let's print here some confirmation. Actually, probably making this more complicated than it should be. Let's make it like this. Trees equal to insert tree, so that here I could get the node pointer to position. If the position's null, then I separate it and I return position, and in other case I return a null. Maybe this is going to be a little cleaner. And now this isn't returning an int anymore, it's returning a node pointer. Okay, so now the f went to the root node because there was nothing in the root node yet. Now, if there is something already in the root node, then I would have to insert it somewhere else. I would have to insert it into a child. So if the position isn't null, then we would need to go to a child position here. And we're going to have trouble with this return in a bit, but let's do the other branch here first. So if the position wasn't null, then we have to compare that if this position has a value that is larger than the present value. So if the new one is smaller, I need to send it to the right. So I will need to insert it to these positions. No, left child. And if it's a larger value, I would need to insert it to the, actually, let's do the equality first. If it's the same value as we already have, we're simply going to increment the counter. No, counter. And do nothing else. Then we're going to have the two other cases, the smaller and the larger. If the current value is larger, then this belongs to the left. And if the current value is smaller, that's going to be simply the else case. Then we're going to be inserting it to the right. And now, why would I want to return values when it wasn't the root yet? Well, I could always actually return the position, but I need to be careful on when do I actually store this position, because my main needs to know where my root is. It doesn't really know where the children are. It always has to go through the root. So I should only assign this value to the root when the root didn't have a value before. And I shouldn't assign it in other cases. So I'm going to make here a temporary node 1. And we're going to put that node is an insertion to the tree. And if tree was null, then tree will point to node. So that only the very first time we create a new node, we're actually going to remember that this is the root. And at all other times, we're simply going to be adding either the counter value, if it's the same letter again, or we're going to creating the left children for the values that are smaller, and the right children for the values that are larger. So let's see how much I broke. Show tree. Use of undeclared identifier tree. I do believe I have here a node pointer tree, but I believe I'm writing the wrong thing here then. No, so pushes on left child. Let's make it smaller to understand what the problem is. Use of undeclared identifier tree. Oh, it doesn't like it that this is called node because node means two different things. Let's call it n. Okay, make this a little bigger again. Let's see how much I broke it. So if I add an F, it creates the F. And every time I add an F, I'm simply incrementing the counter. Now it's showing it twice. It's kind of getting on my nerves that it's showing it twice. Position isn't null. It's going to print the value and the counter. Then it's going to show the left child and the right child. If the position's value is the same as the existing one, then we just increment the counter. In other case, we're making the insertion to the left child. Oh, but now the problem is that we need to remember here that the left child is actually going to be the created node, and the right child here is going to be the created node. So we don't just create it, we also remember where it goes. Okay, let's kill this. Okay, still printing too much. If I add an A is there now once. If I add an H is there once. If I add an F's there more times. Something very fishy with all my printing. I look like I'm inserting, oh, I'm inserting the spaces. It's inserting the enters anytime I press the enter. So let's set another case here. If C isn't a white space character, then we're going to add it to the tree. If it is a white space character, then we're not going to add it to the tree. I'm just checking where does is space come from. Is space comes from C type H. Let's also make them lowercase in case somebody decides to start typing uppercases. Hiding this. Hiding this. Where's my window? Over here. Let's quit this with the dash. Make this a little smaller. Compile again and see if we're any better. 1F, 1A, second F, 1H, 1E, 1F, more H's, 1A. Okay, so now we're looking at the tree every time, but it's really difficult to understand that this is a tree, right? Because they're always printing at the same exact level. So you don't really get to understand that this is a tree. So let's try to track how deep in the tree we are so that we can actually make this a little tiny bit better. So we would here, when we insert a node, we would be inserting it to a depth of 0. But if we're passing it on, we're always going to give one higher value to depth, so that only the root ends up being in depth 0. Everybody else ends up being at depth 1, depth 2, depth 3, etc. So now I could make it so that I could print here stuff in terms of what the depth is. So I could make it so that, let's make an integer counter here, integer I, for I goes from 0 to position depth. I'm so bad at typing. We could just print spaces or dashes or something. Let's just print spaces since dash already means something. Let's quit. It's called position in this routine. Okay, so that's just the F. Now if I add an A, that A now is a child of F. If I make a J, that's also a child of F. And it's always putting the left child first and the right child later. So now let's make a pretty tree here. I'm going to also add a B and a G and a U and a P and a W and an R and a T and a J. So now we can kind of start seeing the tree structure that we are making here, because I can tell that F is the root and it has two children, A and J. A has one child, B. J has two children, G and U. So let me make this a little larger so I can see it, and I'll go to the whiteboard and I'm going to draw this tree. So what we have is I have an F. F has a child A that has a child B. F also has a child J, and there's a G over here. There's a U over here. The children of U are called P on this side and W on this side. P has a child, R. Now it's hard to tell whether it's the left or the right one because it only has one child, but it's going to be on this side because it's a larger, and then a T over here. So this is the part where I actually have to recite the alphabets to know which side they go. And we could improve the printing a tiny bit to make it show whether it's a left child or a right child. So we could add here a little prefix thingy. So we could here, let's say, put that one for left child, that one for right child. And when we print The very first thing we would print would be if we're the left or the right one. Let's actually put it here. So the prefix, I could put it here. And when I call show from the main, I could just give it a space as a prefix. Let's see what this looks like. Broke something. Put this thing outside of the parentheses. Okay, so I'm gonna add the same stuff again. There's going to be an F, and there's going to be an A, and then there's going to be a B. I actually threw the B on the wrong side. The B should have also been on this side. Then we have a J. J is going to have children that are a G and U. Then I'm going to have a P and an R and a T and a W. So now it's a little bit easier to see that F has the children A and J. A is to the left, J is to the right, and then B is to the right of A. For J, it's G to the left, U to the right. For U, it's P to the left and W to the right. And then from P, there's to the right R and then to the right T. Now this just looks a little funny that the root doesn't have a prefix because it's just a space. So let's make a plus there just to make it prettier. I'm writing stuff that doesn't even go, but the program's pretty robust. So it's putting them in the tree now. And the only thing I have left to make this a little less ugly is we have here a malloc for reserving memory. Oh, fuck, I forgot you guys on the whiteboard again. Thank you. So I made it like this. The plus sign shows the root, and this thing is here tell if I'm on the right branch or on the left branch. You guys could just say something, you know, because I can hear you on Discord. Would be so much easier than waiting for me to get back to the computer. Okay, so I want to clean it up so that since we're reserving the memory with the malloc here, when we're done, I would like to free all the memory. So we need some kind of routine. Let's call it erase. And what we would need to do is first say that we're going to erase the children. And once the children are erased, we could erase this position itself. And that should be able to get rid of all the memory we have resolved by malloc. Code might be kind of ugly, but at least it's something. So after we do all of this, before we leave main, it would be nice to free all of it. So we're going to erase tree. And now we need the option that if we erase when it's not even initialized yet, we don't do it if it's null. So here we're just going to add if pos isn't null, then we're going to do this. But we're actually going to do it recursively with the erase so that the children of the children of the children of the children also get erased. And we're going to want to do both the left side and the right side. So only for those that aren't null, we're going to try to erase their children. When both branches of children have been erased, then we try to get rid of the node itself. Let's see how badly I broke it. Let's make the tree on the whiteboard again. I have an F and an A and a B. Then I have a J and a G. Then I have a U and a P and an R and a T. Then I have a W. And then if I leave, I don't get a segmentation fault or anything ugly because it just got erased. So now I have a tiny little tree. It just contains letters, but I have a left and a right branch for the root, and I can have only one child, or I can have leaf nodes that don't have any children. So let's put that into GitHub. And check if we have any immediate concerns about this code. But seriously, guys, you're all on Discord with me. You could just say things. The computer doesn't make any sound. No matter how many times you tag me, it doesn't make any sound. But you can, with your little mouth, say, hi, we can still see the whiteboard. It's a very easy thing to do. And nobody on the stream is going to hear you because you're in my headset, okay? So just tell me if I forget to change the screen, because I've now read it maybe 10 times in total. Okay, so let's going to go over the little pieces here. We have 3 libraries. I'm using one to print, one to manage memory, and one to work with the characters. I have a structure for nodes. Each node can contain a character. It contains a counter of how many times the character has been added into the tree, and it's remembering at what depth are we in the tree. I'm going to go to the whiteboard to show the depth part. So the depth of the root is a 0. Root's children have depth of 1. Their children are at depth 2. Their children are at 3. Their children at 4. And their children at 5. Let me take a photo of this and then I will go back to the computer. Picture. Picture coming up. If I want to erase the memory for a node, I will need to first erase the branches that depend on it. Once the branches have been erased, I can erase the node itself. If I do this in the wrong order, I will lose the information of where the branches are before I actually get to erase them. So that's a recursive routine that's erasing information. We have another recursive routine for inserting the information. When we want to insert a node, we're going to tell the routine, what's the character that we're going to store in this node? We're going to say where we're starting from. We need to tell the program where the root was so that we always use the same tree. And we're going to pass down the information of the depth so that when we're creating the root, it's going to be depth 0 and everything else is going to be at a higher depth. So if there's no node yet, we reserve the memory, we store the value, we set the counter at 1, and we set the depth at the value we received as a parameter to the subroutine. If the position isn't null, then we compare. If the character we want to add is the same one that we already have in this node, we just update the counter and we do nothing else. If it's a smaller value, we will make a new node that's going to be the left child of this node, and that's where we're inserting the value. If the value is higher, we're going to make a new node that's going to become the right child. And that's where we're going to insert it. If we already have a left child, well, that's where we're going then. Actually, this isn't the best way to do this. Let's make a temporary one here as well. If we don't have a left child yet, then the new one we just made becomes the left child. If we already had a left child, we're just keeping it. This might be slightly easier to read. And the same thing here. If we didn't have a right child yet and we just made one, then the one we just made is going to be the right child. But in each case, we're just returning the position we were at. So when we create a new node, the address to which we've created it gets returned so that the one that has the new child can know where the new child is, and that the main routine is going to know where the root actually is. When we're printing the tree, if we are at a non-null position, we're going to print a space for every level of depth of the tree. Then we're going to print a prefix that tells us if it's the root or if it's a branch. If it's a left branch, we're going to send it with a left pointing symbol. If it's a right branch, we're sending it with the right branch symbol. Then we're putting the character stored in the node, and then we're putting in parentheses the number of times this has been added, and this doesn't return anything. We can just put a return there. It's a void routine. Let me take a little screen capture of that one too. Then in the main routine, I have a temporary pointer where I store my tree pointer, the character that I'm reading. While I keep getting repeating here on a true, I read new characters. If I got a dash, I erase the whole tree and I quit the program. If I didn't get a dash, but I got something that wasn't a space, I make it into a lowercase letter. I send it to my tree at depth 0. And I get the temporary pointer as the possibly created node. So now, if I got a created node there and I didn't have a tree yet, then this thing now became the tree. After I've added something to the tree, I'm going to show the tree, and the prefix for the root is always going to be a plus. And then when the root sends the branches recursively to show themselves, it's going to put the prefixes left and right according to the branches. Now, if you have confusions about any of these parts in particular, please write or say a question so that we can discuss the part. Let me make sure I didn't break it and then put it back to the GitHub again. I think I actually broke it. I legit broke it. How did I break it? By assigning the wrong way around. Very clever of me. I think I can actually add lots of things at once. Yes, I can. I have a mega tree. F's been added 7 times. Its left child is a D that's also been added 7 times. Its right child is an R that's been added 6 times. R itself has two children. Left child is J that's been added 8 times. The right child is a Y that's been added 9 times. And then I can erase the whole thing. It's actually kind of fun. Lovely little tree. Little poll. Okay, 4 people are on board. Let's look at the homework and try to understand what's the relationship between this nightmare that I have here and the homework that you guys are actually going to have to do. If I can find the browser window, gotta be this one. So the homework starts with implement a tree. So you might want to maybe watch over what's going on here again if you really didn't understand. We're going to store user data, and we're going to use an alphabetical left to right ordering. The difference is that my data was just 1 character. By the way, according is misspelled here. Let's go fix it. Your data is not going to be just 1 character. Your data is going to actually be strings. And those are going to be case-insensitive usernames. Case-insensitive means you can put it all to lowercase like I was doing. According. Okay, so you're going to be storing usernames. And we are going to store information only in the leaf nodes, and the inner nodes are going to be routers. My code is storing information in all of the nodes. You're going to need to modify my code in such a way that only the leaves are actual users and the inner nodes are going to be router nodes. I'm going to show this on the whiteboard in a little moment here. You're going to be inserting new usernames, and you can also remove a single username if it's not reserved anymore. For each user, you will be storing their password, and if you want to deregister the user, they need to give the matching password. You cannot deregister a user without them knowing the password. Before you write code, I would like you to make some kind of a drawing of what you're planning to program. And that drawing, whether by hand or by computer, please post it on Discord so that other people can see your reasoning and give you feedback. I do not want anybody to be grading codes that haven't been discussed as a drawing on Discord. So when you post it, you're going to take a screenshot of you posting it on Discord as evidence, and you're going to put it in your repository so that everybody's code has actually been discussed. But let me go on the whiteboard and explain this username thing and what do I mean by inner nodes and outer nodes. Okay, so let's say that the first user to register will be Juan. I don't know how to write Juan, and his password is going to be PW123. So we're going to create one single node. It's the root. It's the only node. It's a leaf. That's Juan, password 123. So let's say now we want to register another user. Let's say it's going to be Isabel. So now what we're going to do is think of the alphabet. I's come before J's. So we're going to make here Isabel, and her password's going to be my dog. And we're going to make here the user Juan, whose password is 123. And this is now going to be a router node. And the router node, how do I know it's a router node? I could just set the password to a null so that there is no password. Now, meaning that anything that's alphabetically before Juan is going to be in this branch. Anything that's equal to or larger than Juan in alphabetical order is going to go over here. And why am I doing it this way? Because now if Juan wants to deregister, I would have to move Isabel around if I had left Isabel here and Juan here. But if Juan wants to deregister now, there's no problem. I can just erase Juan and Isabel's still fine. The tree is still fine. So now if, let's say Jose wants to register, Jose comes in the alphabet before Juan. So Jose is going to have to go here. So what do I have to do? I have to duplicate here so that Isabel, my dog, actually moves to a leaf. This becomes a routing node, Isabel, so that Jose, I like turtles, is going to actually be a user here. Then let's say we add Pepe. Okay, so we're going to create a user Pepe, and his password is going to be ice cream 246. Okay, so now I have 2 router nodes and 3 user nodes. I never erase the router nodes. I leave them there forever and forever and forever. When I create new users, I always need to make a split. Because if I now add Raul, I'm going to need to make this Pepe into a router node. I'm going to need to move the Pepe ice cream 246 here. And Raul, I don't know, boss man 17 over here. And the Pepe here becomes a router node, so it doesn't have a password anymore. So now I could deregister, let's say Pepe and Isabel, and nothing happens to the rest of the thing. I remain with 3 router nodes and 2 active users, Jose and Raul. This is what your homework is going to do. We are now polling on whether we are okay with what the hell is going on in this homework. So the very first thing you need to design is what your structure is going to look like. Like here in my code, I designed that my nodes had characters and counters and depth and children. You need to design this to make sure that you're going to be able to store router nodes and user nodes. Users are going to have passwords. Router nodes don't need to have passwords. You're going to need a routine that inserts new users. You're going to need a routine that removes existing users, and existing users are only removed if provided with the matching password. If you're trying to remove an existing user with a mismatch in the password, you're just going to get an error message. One person has a question, one person is okay, 22 people need more time to process this. So let's look at the question. Daniela, you can type or say your question. I'm going to modify my own code a tiny bit to make it a little easier to deal with this router node stuff. I'm going to add in my code that the leaves are going to be printed in a specific way. So Daniela, when a user doesn't want to use your thing anymore, let's say they delete their Facebook account, you're going to remove them entirely. So it means that their username is no longer reserved and their password is no longer stored. But you will remain with the router nodes that organize the structure in which the other usernames are stored. So even if there's no user Daniela anymore, they might be a Daniela as a router node saying which users come before Daniela in the alphabet and which ones come after. I'm going to modify this code a tiny little bit, just make the leaves look different. How do I want to make the leaves look different? I'm going to print them a suffix. So now it added all those letters, and all the nodes that are leaves actually have a little hashtag showing that there's nobody depending on them anymore. I'm going to modify the code a second time so that when I add several things at once, I don't actually get to see the tree. Let's make it so that showing the tree is a separate option. That I only show the tree when I type an exclamation. So what you're going to have is a user interface, and your user interface is going to be pretty simple. We can simulate it on Discord. Let me just add this new version to GitHub. So basically, we could have something like a prompt. You could ask for the user to give an operation, and the user could type stuff like add Jose, I like dogs, or delete Daniela, confused, or add Juan, tigres. And then if you try to add a second Juan, you would get something like a warning. And then if you try to delete something that doesn't match the password, you could get an error. Then if we write stuff correctly, we could get like a confirmation message. And then we could type something like view, and we could get the tree of all the users that we have. If you want to be really fancy, you could print them in alphabetical order by traversing the tree in a very specific way. I'll actually show you guys how I can print the letters in alphabetical order from my code so that you can make it a little better on yours. Let's add an option here. My cats think they're starving. Let's make it a question mark. I'm really good at typing print instead of printf. I'm just going to use this text here as input. Okay, so let's look at it first. That's what it looks like, and this is what it looks like in alphabetical order. I just accidentally put this thing there. So now the letters come in alphabetical order, because if I always print the left branch, then the inner node, and then the right branch, they're going to come out in alphabetical order, like no matter what. So let's come out of here. Let's do this again. Let's take a long piece of text. Let's get some Bible. So I have this tree now. And in alphabetical order, the letters are like this. So there are not a lot of Q's in the Bible, not a lot of Z's either. More questions? We have 6 more minutes left for any kind of imminent panic. Let me get you guys the example I use for the discrete math students for binary trees with numbers, if you guys want to click on it for a while. So I've made this for the discrete math students. They can just put numbers here and it draws the binary tree. Yeah, so to the question of Edgar, you need to discuss a plan for your program. I don't really care what kind of a graphic it is. I just want to see how you think about it, like what you have designed before you start programming. Like I want you to try to design it first and program it later so that you don't just start typing like literally random shit, but you actually think about what do I need? What pieces do I need? What program's going to be? What part of the program is calling out of the part of the program? Which parts are recursive? Who's keeping track of which information? Like try to make a plan, any kind of a plan, and then first post the plan on Discord. Hopefully someone's going to give you some feedback or questions, and then you start programming once you've actually thought about what you're going to program. If you've kind of understood and you think you'll be fine with the recording, you can go now. I'm going to turn off the Twitch stream, but I'm going to stay on Discord for the wonderful 3 minutes that we have remaining in case you guys have more questions. And please, as soon as you have time to think about this, make any kind of a drawing. I don't care if it's ugly. I don't care if it makes any sense. Try to think about what you're going to program and then post a picture. I would recommend doing at least the first one of the mini exercises before you start programming or designing so that you can be sure that you sort of understood structures. Because this, if you don't understand structures and if you don't understand pointers, you're going to have a very bad time.